Speaking of time, do you believe time to be, well, maybe you don't, let's not say believe. When you were playing with some ideas earlier and you're saying, well, time may be emergent, do you also believe space to be emergent? Do you believe space time itself is emergent?
Yeah, I mean, if time is emergent, it's hard for me to imagine that space is not emergent too. Again, anybody who's spent a little time thinking about the insights from Einstein on recognizes that space and time are so deeply and intricately interwoven into the fabric of space time that sort of pulling one apart and imagining it has different properties, space and time have different properties. It's not impossible, but it does fly in the face of pretty much everything we've learned in the last 100 years. So I certainly do envision that if there's a realm of reality in which time does not apply, because as we were saying before, the conditions haven't yet allowed for a conception of time to emerge, the same would almost certainly be true of space. So the real way of saying it is there a realm of reality in which there's no conception of space time? And it's hard for me to imagine what that is, but that's because I've got this brain that is constrained by what my ancestors did. And that brain is one that is so tied to a conception of reality in which space and time are the architecture within which events take place, that it's really hard for us to think about a reality in which there isn't space time. And so I wish I could give some really good example or insight into what that would be like, but it would be some kind of reality in which the language that we use would not talk about when things are happening, and the language that we use would not talk about where things are happening. The language would somehow be beneath that, more fundamental than that. And it's not that scientists don't have some ideas for what this might be like, but I'd say that we do lack the deep picture and the deep story of how we would really articulate and navigate a reality absent space-time.
Have you had a chance to go through Wolfram's theory, his project on physics?
Wish I had, yeah, I mean, Steve's a great guy and he's a friend, and we talk about things on occasion. And I wish I had more time to spend with him, because it's always illuminating when we do spend some time together. But I don't feel like I've fully grasped the approach that he's taking. And
Why?
I can absolutely throw this on myself. So it could well be limitations in my own thinking and limitations in the amount of energy and effort that I've expended to understand his approach more fully. But I get stuck on trying to really understand whether the formalism as he envisions it, is it actually fundamentally different from the more traditional formalism? He would say yes, as far as I can tell. But as I have looked at it on occasion, it has struck me that it's not obvious to me that it is as different as he suggests. And again, I could be wrong on this. And it could be that I just haven't put enough effort or energy into it. I'm glad that he's pursuing his approach. It's not within the confines of the traditional established environment. He's not doing it inside of a physics department or a math department. He has the resources and the creative energies to make his own environment and find his own collaborators, and more power to anybody who has the capacity to do that. Whether it's going to bear the fruit that he envisions, I don't know, but I'd say the same thing about what we're doing here. Like, we've been beating down on string theory, since, 1984, at least, the big first revolution. But since 1968, if you want to go further back to the first glimmers of string theory, And where are we now? 2023? That's a lot of years, right? So you can say the same thing, so I don't feel qualified to really judge the approach, but I just feel that I haven't fully wrapped my head around whether or not it's fundamentally different from what we do.
Quite a few thoughts. Firstly, what progress has been made in string theory in the past, say, 2 decades?
Yeah. Well, that's a nice big chunk of time. And I'd say, the big thing in the last 2 decades has been the recognition that there's a connection between gravity and quantum mechanics that I don't think we sufficiently appreciated 20, 25 years ago. I mean, take my book just as one moment in time, a snapshot in the Elegant Universe. That was published in 1999. And in that book, I very clearly lay out there's this theory called general relativity, describing gravity, the big stuff. I lay out how there is this other theory called quantum mechanics, describing the small stuff. And we want to put them all together to have a unified theory of the big and the small, but we're having trouble doing that. And then I go into the book and how string theory seems to be making progress in putting the big and the small together. If I was writing that book today, and in some sense I am, because I'm adding a chapter for the 25th anniversary of the Elegant Universe. And one of the things that I'm emphasizing is there's now a lot of evidence that gravity and quantum mechanics, in some sense, are kind of the same theory. They are already, in some strange sense, combined. And this was completely unexpected based on anything that we knew 20 plus years ago. So within, for instance, general relativity, there are these structures you made reference to, one of them earlier, called wormholes, which are tunnels in the fabric of space going from one space-time location to another through a kind of shortcut. That's general relativity. In quantum mechanics, there's this weird thing called quantum entanglement, where two widely separated particles can act as though they're right next to each other, even though they can be on opposite ends of the universe. And really, nobody thought there was a connection between these two ideas until people like Lenny Susskind and Juan Maldacena and a variety of other influential scientists, too many to name them all, gave evidence that in some sense, wormholes and entanglement are kind of the same thing. They kind of feel the same, if you think about it. Wormhole, it's connecting one point in space-time with another through a shortcut. Entanglement, it's connecting one particle in space-time with another particle, in some sense through a shortcut, because they're acting as though they're right next to each other. And so this is the beginning, the tip of an iceberg of a deep and very powerful story, which is showing that structures in general relativity and structures in quantum mechanics are already deeply connected and deeply entwined. And so the unification program may ultimately not be described in terms of putting gravity and quantum mechanics together the way I described it, and many did, of course, in the earlier days, but it may be more deeply understanding general relativity, more deeply understanding quantum mechanics, and more deeply understanding how they are part and parcel of the same theoretical structure.
If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.